right, welcome back. In section 5.3, we're going to meet the fundamental theorem of calculus. And technically, we've met these ideas in the previous section, but this is where we sort of formalize those ideas. So the first statement of the fundamental theorem of calculus, or FTC, part 1. There are two main parts to the fundamental theorem. The informal way to say this is just for any well-behaved function f, smooth and continuous, and any base point a, the area function is an antiderivative of f. So we saw that in the previous section where we talked about the area function and we talked about how it does give us the antiderivative. Now, the formal way to say that with notation is this. Let f be a continuous function defined on an open interval I containing a. The function a sub f with the rule the area function equals the integral from a to x of f of t dt is defined for every x in I, and when you take the derivative of it, you get the original function back. Bear in mind that the area function is an integral, and that's sitting right here. So what the fundamental theorem of calculus is basically establishing is that if you take the derivative of an integral, you get the original function back again. So taking a derivative and taking an integral are opposite operations. Okay, so again, we've met that idea in the previous sections. Now, the power rule for derivatives, I want to go back and review because we're going to meet the power rule for integrals, but it's really only going to make sense if you remember your power rule. The rule is written out here in symbols. We'll just go ahead and start doing one. So the first function I ask you to take the derivative of is x to the fifth. Power rule says you're going to take the exponent and make it the coefficient in front of the term, and then lower your exponent by 1, subtract 1. Okay? Super easy, right? If you take the derivative of negative 3x to the fourth, if there's already a coefficient in front, when you bring that exponent down, you multiply them. So 4 times negative 3 is negative 12, lower my exponent by 1. And here's a similar example, except we now have a constant term added on. So the derivative for negative 3x to the fourth would be the same. We just go term by term, and when you take the derivative of a constant, that does become 0. So it disappears off of our derivative function. Now, what I want you to think about is the fundamental theorem of calculus is saying we can start with this derivative and get the original function back again, right? That's what it means to integrate. But what I want you to observe is in example 2 and 3 here, we started with the same derivative function, but it came from two different original functions. So when we integrate, when we say we're finding the antiderivative really is not just one function. It's a family of functions. I know when I integrate my negative 12x cubed that the antiderivative for that is negative 3x to the fourth. What I'm not able to determine is the presence of any constants on that antiderivative. So the antiderivative being negative 3x to the fourth is our way of saying the antiderivative definitely includes that, but it could be negative 3x to the fourth plus 1, plus 2, plus 7, plus pi, plus negative 4. So the antiderivative is that base function. And then to that, you're going to see that when we integrate, we'll put a little plus c on the end of it. And that's indicating that the antiderivative is really that family of functions. It's not just the function negative 3x to the fourth, but it's negative 3x to the fourth plus some constant. Here's what the power rule for integrals looks like. And we're saying it here in notation, but the idea is it needs to be the reverse of the power rule for derivatives. Rather than bringing the exponent down and having it multiply the coefficient, you're going to bring the exponent down and divide by it after you've added on 1. because with derivatives, we lower exponents. With integrals, we increase them. And we're going to put this plus c on the end of it because that will allow us to, again, recognize this is a family of functions, not just a single answer is possible. So that's what this node is getting to. If you can find one antiderivative, you've essentially found all of them because they're all going to be part of this family where they differ by a constant. Okay, so let's take a look at a couple of examples of power rule for integrals. So if I want to take the integral from x to the 7th dx, I want to find the antiderivative. The power rule says that we're going to go ahead and increase the exponent by 1. And again, instead of multiplying that by the thing in front, we're going to divide by it. It's as simple as that. And we're going to put that plus c on it because there may have been a constant. Now, given more information, it's actually possible to track down your constant, and we'll get to that eventually. All right, in the next example, the integral in part B, you work term by term. So you begin with 5x cubed. You increase its exponent by 1, which is the 4. You're going to keep that 5 just sitting there, but we are going to divide by 4, by our new exponent. Add to that, we're going to take x squared, increase the exponent by 1, make it x cubed, and divide by that exponent. And this last one, if you had a constant, the constant -1 is the same as writing it as -1 x to the 0 power, because anything to the 0 power is 1. 1 times -1 gives you -1. So you want to keep that in mind because when we increase the exponent by 1 here, it's going to become, we're going to have the -1, and we will have an x to the 1st power. We just don't usually write that 1. And I would technically be dividing that by that new exponent of 1. Now, again, in this situation here, it's much more likely that we would write this answer as minus x. And of course, don't forget our plus c. All right, the antiderivative. Find the value of this integral. This one, before we can integrate it, we've got a square root here. And I have told you that we're practicing the power rule for integrals. So what gives? Well, as calculus students, you should be very familiar with the fact that the square root of x is equivalent to x to the 1/2 power. You're going to want to write it that way first. We have a rule for converting roots to fractional exponents. If you have a root of x, and let's say that it's the nth root, and x is to the m power, you can rewrite that as a fractional exponent where you bring this n around to become the denominator for the exponent on x. So that's what we did here, because technically on this square root, the index of that radical is 2. This is x to the 1st power, so we make the fraction 1/2. Now we're ready to integrate this, and you've got to be a little bit fraction friendly because we have to add 1 to that exponent. So if you're going to take 1/2 and add 1, you of course have to do that with a common denominator. 1 can be rewritten as 2/2, which means that sum becomes 3/2. So we're going to have x to the 3/2 power divided by 3/2. But that's kind of a complex fraction. That's a fraction within a fraction, so we don't typically leave it that way. Instead, dividing by a fraction is the same as multiplying by its reciprocal. So in other words, you make the reciprocal of what you're dividing by, put it next to your variable, and of course, always the plus c. So these are two equivalent forms. This second one is what's preferred. I threw in a cosine example. Hopefully you do remember that the derivative of sine is cosine. And remember, since we're integrating, we're just kind of going backwards. So if we integrate cosine, we should get back the function sine of x plus c. All right, now the second fundamental theorem of calculus helps us now take that step of finding the value for what we call a definite integral. This is where I say, okay, I want to get specific. I'm going to look at the area under my curve from here to there. And because we're getting specific and finding it from here to there, and it's an area, it's going to just reduce to being a number. So the fundamental theorem of calculus, the part 2, this is the one that we rely on most heavily, is if you have a continuous function, capital F can be any antiderivative of f, then when you find that antiderivative, you substitute in the upper limit minus the lower limit substituted in. And if you want to see a proof of this, there is one provided in your textbook. All right, so now we're going to find the value of what we call definite integrals, because we know it goes definitely from here to there. And the way that we do that is, first, we need to know what this capital F function is. So we need to find the antiderivative. Okay, so I'm going to use the power rule on negative 2x. I'm going to keep the negative 2. I'm going to increase the exponent on the x to a 2 and divide by that new exponent. Now, I'm not going to go ahead and put a plus c here because we're going to be able to find the numerical value exactly by substituting. So it's common to use square brackets here. And on the outside of the square brackets, we put the lower and upper limits of integration to remind us that the next step is going to be plugging in these values. Now, I do recommend that you simplify your antiderivative before you do that substitution. So I can cancel these 2's and I've got negative x squared. And I'm supposed to find the value of that function from 1 to 4. So we're now working on this side of the fundamental theorem. We know our antiderivative. You will substitute the upper limit first, and then you will substitute the lower limit and subtract it. And I'm using a lot of parentheses here because we've got negative signs flying around and we've got to be really careful with our substitutions. So I'm going to square 4. You always square before you negate. So this becomes 16 and the negative sign makes it negative 16. I'm going to subtract, square the 1, then negate. So that becomes negative 1. And negative 16 minus negative 1 becomes negative 15 is the numerical value. And so what that tells us is that this, the shaded area for this particular function is going to be located below the x-axis because it is negative. So just to kind of confirm for you that the fundamental theorem of calculus really does work, I went over to Desmos.com, which is a really nice graphing calculator, web-based application. It also is an app for smartphones and devices. I went over here and I had it graph negative 2x and I had it shade the area under the curve, which in this case is actually above the curve because we always go from curve to x-axis. And I had it do that from 1 to 4. This shaded area is supposed to be 15 units, and so this shaded area is supposed to be 15 square units, and it's negative because it's located under the x-axis. This shape, of course, is a trapezoid. So if we use our techniques from the previous section, the height of this particular trapezoid is here, which is 3 units. Remember, the bases are the parallel sides, so this base is 2 plus 8 units. It's located below the x-axis, so I'm going to put a negative on there, and lo and behold, we do get negative 15. Okay, so the fundamental theorem of calculus is doing the work that we did geometrically in the last section in an algebraic way. All right, let's go to example B. I'm going to find the integral from 0 to 2 for this function, 5x to the 4th plus 3. Begin by finding your antiderivative. Keep your coefficient increase your exponent, divide by that new exponent, plus, and a constant term will always become linear when you increase its exponent. In other words, it's going to be 3x. I can put divided by 1, but there's really no need for that. So that's my antiderivative. Now, one note about notation, I do put square brackets on both sides of my antiderivatives. However, it is correct notation to also just put it on one side. Sometimes you'll see it as a single square bracket like that. Sometimes you'll actually just see it as a vertical line. All of these are acceptable notation. My OCD just likes having brackets on both sides of it. So you'll see that when I simplify this antiderivative and rewrite it, getting rid of the 5's, I like the square brackets on both sides. But whatever you're used to. And then after that, we're going to substitute our limits of integration all the way through, beginning with the upper limit. So put in 2 for the x's in both spots. And this is where, honestly, if I was doing this, I don't even bother writing that substitution because mentally I'm already ahead of myself. I know 0 to the 5th power minus 3 times 0 will be 0. So really, this integral takes on the value of just this first term, which is 32 plus 6, which is 38. So that would be the area under the curve. So this one, we know the shaded area would be above the x-axis. For our next example, we're taking the integral from -2 to 0 of the cube root of x. Now, just like when we had a square root, we had to rewrite it as a fractional power. We need to take and rewrite our cube root as a fractional power. So I'm going to keep the integral symbol because I have not yet integrated. The cube root of x is the same as x to the 1/3 power. Okay, so now I am ready to use my power rule for integrals to find the antiderivative. I'm going to increase my exponent by 1. Now, again, kind of working off to the side here, if I'm going to add 1 onto 1/3, I'm going to do it as 3/3 with a common denominator. So my new exponent should be 4/3. So it's going to be x to the 4/3 power. And again, instead of dividing by 4/3, I'm going to go ahead and automatically write that as being multiplied by the reciprocal 3/4. So that's my antiderivative. It's supposed to go from -2 to 0. Now, again, kind of like the last problem here, I kind of think ahead and it's like, okay, well, if 0 to the 4/3 power is going to be 0 times anything is going to be 0. So my whole first term really is just going to be 0. I do want to make sure I remember to write it because then technically we subtract -2 substituted in. So we don't want to lose that there's this subtraction happening. So I have 3/4 of -2 to the 4/3 power. All right, so when I do 0 take away that, it's just going to be a negative result. So we're going to have -3/4. I'm going to take this -2 to the 4/3 and rewrite it in its radical form. So that would be having a -2 to the 4th power under the radical. I'm not really going to do much more than say, okay, -2 to the 4th should be 16. I'm going to keep it under the radical because the cube root of 16 is not a particularly nice number. So that's as simple as I'm going to take this one. Of course, I could go to a calculator and get a decimal approximation. And lastly, when you're working with integrals, just so you know, if you have a constant multiplier on your integral, you can just basically let that come along for the ride. So what I mean by that is I'm going to keep the 2 in front. I'm going to figure out what my antiderivative is. Now, the derivative of sine is cosine. The derivative of cosine is negative sine. And hopefully you're familiar with the Greek letter theta here for an angle. So if I'm going to go backwards and I'm going to integrate sine, notice how you change the sign from the original function to its derivative. So when you integrate and go backwards, you also need to do a sign change. So my antiderivative, in other words, is going to be negative cosine of theta. We're supposed to go from 0 to pi. Still keep 2 in front as you go about the substitution of pi. And again, I'm going to be really careful with my parentheses here because of negative signs, subtraction signs, there's a lot going on. I do expect at this stage in the game that you are familiar with some basic values of the cosine curve in radians. So the way that I think about this without using a calculator is I know the cosine function has this general shape as it goes from 0 to 2 pi. I know that pi is halfway in between, so I just visualize this. So I need cosine of pi. Cosine of pi hits its lowest level down here at -1. So I have the negative sign, and cosine of pi is -1. Again, being very careful with parentheses. And then I'm supposed to subtract from that. At 0, cosine is at its highest point. It's at 1. So it's a -1 when we put the negative sign onto it. So our final answer will be a -1 is +1. This minus a -1 also changes to a +1. And we have 2 times 2, which is an area of 4. So that's a basic introduction to the fundamental theorem of calculus. There is more to come in the next video.